In this module, we'll learn some essential debugging techniques. We'll start with the basic process that we can use for tackling any technical problem. Then, we'll look at different ways that we can approach understanding what's going on and finding the root cause of an issue, including using a process called binary search to troubleshoot problems. Along the way, we'll talk about a bunch of examples of real-world problems and how to apply the techniques to solve them. The techniques we'll look at are reusable and will let you solve almost any kind of technical problem that you might face in the future. We'll keep applying them throughout the course as we explore different issues that can affect us or the users we're supporting in different ways. As with any other skills that you've learned throughout this program, the best way to get good at something is practice. So, at the end of the module, you'll have the opportunity to apply these techniques and try solving a technical issue yourself on a virtual machine running Linux. Finding the solution to a problem can sometimes take a really long time. And while I don't know if anyone loves troubleshooting, I definitely enjoy solving problems. Dealing with software is like trying to solve one giant puzzle. It can sometimes be frustrating when we can't find the right pieces. But it's super exciting when everything finally fits together. If everything I did worked right away, then it wouldn't be fun anymore. I love the challenge. Let's get you started. Throughout this course, we'll be talking about debugging and troubleshooting. So what's the difference between them? We say that troubleshooting is the process of identifying, analyzing, and solving problems. We can use the term troubleshooting to refer to solving any kind of problem. In this course, we'll focus on troubleshooting IT-related problems. They could be problems caused by hardware, the operating system, or applications running on the computer. They could also be caused by the environment and configuration of the software, the services the application is interacting with, or a wide range of other possible IT causes. On the flip side, debugging is the process of identifying, analyzing, and removing bugs in a system. We sometimes use troubleshooting and debugging interchangeably, but generally, we say troubleshooting when we're fixing problems in the system running the application, and debugging when we're fixing the bugs in the actual code of the application. There are lots of tools that we can use to get more information about the system and what the programs in our system are doing. Tools like tcpdump and Wireshark can show us ongoing network connections and help us analyze the traffic going over our cables. Tools like PS, top, or free can show us the number and types of resources used in the system. We can use a tool like strace to look at the system calls made by a program, or ltrace to look at the library calls made by the software. Don't worry about memorizing them. We'll talk about each in detail in our real-world examples. When debugging the code of a program, we can combine these tools with specific debugging tools developed for the programming language used to write the application. Debuggers let us follow the code line by line, inspect changes in variable assignments, interrupt the program when a specific condition is met, and more. On top of that, if we can modify the code, we can change it so that it provides more logging information. This can help us understand what's going on behind the scenes. Both troubleshooting and debugging are a bit of an art. In those fortunate cases when you've seen the problem before, you might immediately know what the solution is. But usually, figuring out the problem and its solution requires some creativity. We need to come up with new ideas of what could be failing and ways to check for that. And once we know what's failing, we need to imagine how to solve it. To take it a step further, once we've solved a problem, we can start thinking about how to prevent it from happening again. I remember a tricky debugging session that I had on my last team. We recently added integration tests to one of our pipelines to make sure the service worked correctly before automatically building and deploying a new version. The test ran fine for about a month, and then it started to fail. Since this was an integration test that would prevent a broken version from getting released, I was really surprised to discover that the broken code was actually already live in the production server. I looked at tons of logs and spent a long time following what the code did. Finally, I noticed that the problem was that the tests were running against the production instance instead of the test instance as we originally intended. In other words, the tests would pass as long as the production instance was working fine, and would break when the production instance was broken. Not what we wanted at all. To fix the problem, I had to figure out why the test code didn't connect to the test instance that we were creating inside the integration test. After a lot more investigation, I discovered that the test instance was failing to start because the execution path was incorrect. To fix this, I ended up modifying a library provided by a different team to pass the right parameter, and voila! The test started running against the code in the test instance, not the production instance anymore. When troubleshooting or debugging, we come across surprising situations. Things aren't working as expected, and we need to understand why and figure out how to solve it. As we called out, in this course, we'll look into a bunch of different techniques to understand and solve technical problems. While we'll sometimes focus on system side and sometimes on the coding side, most of the techniques that we'll cover can help us solve any technical problem. Up next, we'll talk about the steps we need to take to solve any kind of technical problem. There's a wide range of different technical problems that you might face as an IT specialist or systems administrator. But fortunately, there's a set of steps that you can usually take to solve almost any technical problem. The first step is getting information. This means gathering as much information as we need about the current state of things, what the issue is, when it happens, and what the consequences are, for example. To get this information, we can use any existing documentation that might help. This can be internal documentation, manual pages, or even questions asked on the internet. One super important resource to solve a problem is the reproduction case, which is a clear description of how and when the problem appears. The second step is finding the root cause of the problem. This is usually the most difficult step, and throughout this course, we'll discuss a lot of possibilities on how to get there. But the key here is to get to the bottom of what's going on, what triggered the problem, and how we can change that. The final step is performing the necessary remediation. Depending on the problem, this might include an immediate remediation to get the system back to health, and then a medium or long-term remediation to avoid the problem in the future. And while these are 3 basic steps of problem solving, they don't always happen sequentially. It's pretty common that while trying to find the root cause, we discover that we need even more info about the current state. So, we gather more information until we find the answer we're looking for. Or we could understand the problem just enough to create a workaround that lets our users get back to work quickly. But we'd still need more time to get to the root cause and prevent the problem from happening again. Preventing the problem from recurring can sometimes feel like a hassle, but it can actually save us and our users a lot of valuable time. This way, we avoid having to solve the same problem over and over again. Throughout the whole process, it's important that we document what we do. We should note down the info that we get, the different things we tested to try, and figure out the root cause. And finally, the steps we took to fix the issue. This documentation might prove invaluable next time a similar issue pops up. Imagine a user asks you for your help because their computer is unexpectedly shutting down. Computers shouldn't shut down on their own, but the problem could be a hardware issue, a software issue, or even a configuration issue. So the first thing to do is to get more information. You'll want to know things like when it happened, what the user was doing when it happened, and how regularly it's happening. You'll also want to look at the computer logs to check if there are any interesting errors. And if any aren't totally clear, you can look them up on the internet to see what they mean. In our example, say you found a line in the logs that says the temperature threshold was exceeded, and so the computer shut down. That's useful information. You know why the computer shut down, but you don't know why it overheated, so you'll need to keep investigating. After not finding anything else interesting in the logs, you decide to check if it's a hardware issue. When you open up the computer, you find that the fan that's supposed to cool down the CPU is full of dirt, and so it isn't spinning properly. Aha! That's the root cause of the problem. Now, the short-term remediation is to clean up the fan so that it can spin again and the computer doesn't overheat. But what's the long-term remediation? In this case, it would be deploying monitoring on the computers to make sure you get notified early when they're overheating. Long-term remediation would also include checking if you can reduce the amount of dust in the air so that there's less chance of this happening again. Up next, we'll put these steps to the test by applying them to solve a practical example. Say a user contacts us to let us know that a certain application fails to open. As we called out earlier, the first thing to do is to get more information about the conditions that cause the failure, what the error is that the user is getting, and then check if we experience the same failure. By asking for these details, we discover that a new version of the software was recently released, and when we upgrade to this new version, we can reproduce the problem on our own computer, like this. We see that when we try to run the program, it prints no error at all. It just exits immediately. We need to figure out what's going on, even if there's no error message. There are a bunch of tools that can help us better understand what's going on with the system and with our applications. With the help of these tools, we can extend our knowledge of a particular problem, view the actions of the program from a different point of view, and get the info we need. Among these tools, itrace lets us look more deeply at what the program is doing. It will trace the system calls made by the program and tell us what the result of each of these calls was. So, to figure out what's up with our program that's failing to open, we'll itrace the failing application. Whoa, that's a lot of output. The itrace command shows us all the system calls our program made. System calls are the calls that the programs running on our computer make to the running kernel. There are loads of different system calls, and depending on what we're trying to debug, we might be interested in some more than others. If you want to understand what these system calls are, you can read more about each of them in the corresponding manual pages. But before we jump into that, let's make this output more manageable. We could pipe the output to the less command, which we could use to scroll through a lot of text. Or we could use the -o flag of the itrace command to store the output into a file, and then browse the contents of that file. The -o flag lets us refer back to the file later if we need to, so let's go with that one. Okay, now we can read the generated file using whichever program we prefer. Let's open it with less. We'll go to the end of the file, pressing Shift-G, then scroll up to see if we find anything suspicious. All right, close to the end of the log, we can see that the application tries to open a directory called .config purplebox, which doesn't exist. Let's look at this line in a bit more detail. The name of the system call is openat, one of the calls used to open files or directories. The content of the call shows the parameters passed, including the path that's being opened and a bunch of flags. In particular, the O directory flag tells us that the program is trying to open this path as a directory. The number after the equal sign shows us the return code of the syscall. In this case, it's -1. So the program is trying to open this directory, and it turns out it doesn't exist. Since this is happening shortly before the program finishes, it's a likely candidate for the root cause of the issue. Let's create the directory and try to start the program again. The .config / purple box. Success! This time, the program works just fine. Let's recap what we did. First, we got some information from a user telling us there was a change in the new version, which was causing a problem. To investigate this, we reproduced the problem on our own computer. Then, we got more information on what was going on by using the itrace tool, which lets us see the system calls made by a program. We found a suspicious error that said a directory didn't exist. We created the directory to check out what would happen when it did exist, and the program worked correctly. So we've identified the root cause of the problem, which is the missing directory. Now we can go ahead and remediate the issue. The immediate remediation is to tell the user to create the directory so that they can get back to work quickly. The long-term remediation is to contact the developers of the software to let them know that the program will fail to start if the directory is missing. This gives them a heads up about the problem so they can fix it in the next version. And what about the documentation? We should note that this version of the software won't start if that directory doesn't exist. That will help others facing the same issue to quickly find out the solution. In this example, we were able to use itrace and quickly identify what the problem was. As we called out, the first step to solving a problem is getting enough information so that we can understand the current state of things. To do this, we'll need to know what the actual issue we're solving is. This starts when we first come across the issue, which can be through a report by a ticketing system or by encountering the problem ourselves. When working with users, it's pretty common to receive reports of failures that just boil down to, "It doesn't work." These reports usually don't include a lot of useful information, but it's still important that the problem gets reported and solved. Which information is useful or not might depend on the problem. But there are some common questions that we can ask a user that simply reports something doesn't work. What were you trying to do? What steps did you follow? What was the expected result? What was the actual result? If the ticketing system your company uses allows this, it's a good idea to include these questions in the form that users have to fill out when reporting an issue. This way, we save time and can start asking more specific questions right away. Otherwise, these are almost always going to be the first questions you ask. Another thing to keep in mind is that when debugging a problem, we want to consider the simplest explanations first and avoid jumping into complex or time-consuming solutions unless we really have to. That's why when a device doesn't turn on, we first check if it's correctly plugged in and that there's electricity coming from the plug before taking it apart or replacing it with a new device. Say you get a call from a user that tells you the internal website used by the sales team to track customer interactions doesn't work. The user is super stressed because they need to access the information on the website for a meeting happening in a few minutes. So you tell them that you'll look into the problem right away, but that you need more information. What were they trying to do? The user tells you that they're trying to access the website. What steps did they follow? They tell you that they opened the website URL and entered their credentials. What was the expected result? They expected to see the sales system's landing page. What did they get instead? The web page just keeps loading. It stays blank forever. Okay, so now you've gone from "it doesn't work" to "when I try to log in, the page keeps loading and never shows the landing page." That's great. Now that you have a basic idea of what the problem is, it's time to start figuring out the root cause. For that, you'll apply a process of elimination, starting with the simplest explanations first, and testing those until you can isolate the root cause. For example, you check if you can reproduce the issue on your own computer. So you navigate to the website, enter your credentials, and sure enough, the page just keeps loading, never showing the landing page. This is enough information that you can tell the user that you'll work on it and investigate on your own. There's no need to keep them on the line. By reproducing the problem on your computer, you've taken a simple and quick action that rules out the user or the user's computer as the cause of the problem. This cuts the troubleshooting process in half, since you now know there's a problem with the service and you can focus on solving that. Before jumping into the server that's hosting the application, you run a few quick checks to verify if the problem is isolated to that specific website or not. You check if your internet access is working successfully by accessing an external website, which loads just fine. And then you check if other internal websites, like the inventory website or ticketing system, are working okay. Doing this, you discover that while the ticketing system loads with no issues, the inventory website never finishes loading. It turns out both websites are hosted on the same server. Again, it's important to highlight that doing these quick checks to verify that the internet works correctly and which sites are affected by the problem helps you isolate the root cause. By looking at possible simple explanations first, you avoid losing time chasing the wrong problem. At this point, you know that websites running on a specific server are failing to load, while the rest of the systems and the internet are working correctly. Next step, you need to check what's going on that server. The server running the websites is a Linux machine, so you'll connect to it using SSH. You run the top command, which shows the state of the computer and processes using the most CPU, and see that the computer is super overloaded. The load average in the first line says 40. The load average on Linux shows how much time a processor is busy in a given minute, with 1 meaning it was busy for the whole minute. So normally, this number shouldn't be above the amount of processors in the computer. A number higher than the amount of processors means the computer is overloaded. You know this computer has 4 cores, so 40 is a really high number. You also see that most of the CPU time is spent in waiting. This means that processes are stuck, waiting for the operating system to return from system calls. This usually happens when processes get stuck gathering data from the hard drive or the network. By looking at the list of processes, you realize that the backup system is currently running on the server, and it seems to be using a lot of processing time. Backing up the data on the system is super important, but currently the whole system is unusable, so you decide to stop the backup system by calling kill-stop. This will suspend the execution of the program until you let it continue or decide to terminate it. After doing this, you run top once again, and you see that the load is going down, and so processes are no longer stuck waiting for I/O. Then, you try logging into the website, and this time, the landing page loads. Success. You let your user know that they can use the website once again. At this point, you've applied the immediate remediation. We'll talk about long-term remediation in a later video. Before moving on to the next topic, imagine that the following week, another user calls you and tells you the Cells website doesn't work. Remembering the previous incident, you tell them you'll fix it right away. You SSH onto the server and try to find the backup process to stop it. But it's not running. Oops, you forgot to ask the user what they meant when they said it didn't work. When you call back to ask them, they tell you that they're trying to generate a monthly sales report, and they get an error saying the product category column doesn't exist. Totally different problem, totally different actions to take. So remember to always have a clear picture of what the problem is before you start solving it. Up next, we'll talk about what a reproduction case is and how to come up with it. When we're dealing with an issue that's tricky to debug, we'll want to have a clear reproduction case for the problem. A reproduction case is a way to verify if the problem is present or not. We'll want to make the reproduction case as simple as possible. That way, we can clearly understand when it happens, and it makes it really easy to check if the problem is fixed or not when we try to solve it. Sometimes, the reproduction case is pretty obvious. In our example where the program failed to start because of a missing directory, the reproduction case was to open the program without that directory on the computer. On our overloaded server example, the reproduction case for the failure was to try to log into the website and see the loading page. But sometimes, the reproduction case might be much more complex to discover. Imagine you're trying to help a user with an application that won't start. This time, when you run the same version of the application on your computer, the application starts just fine. So you suspect that the problem has to do with something in the user's environment or configuration. There could be a bunch of reasons why this could happen. It could be problems with the network routing, old config files interfering with a new version of the program, a permissions problem blocking the user from accessing some required resource, or even some faulty piece of hardware acting up. So how can you figure out what's causing the problem? The first step is to read the logs available to you. Which logs to read will depend on the operating system and the kind of application that you're trying to debug. On Linux, you'd read system logs like varlog syslog, and user-specific logs like the .xsession errors file located in the user's home directory. On Mac OS, on top of the system logs, you'd go through the logs stored in the library logs directory. On Windows, you'd use the event viewer tool to go through the event logs. No matter the operating system, remember to look at the logs when something isn't behaving as it should. Lots of times, you'll find an error message that will help you understand what's going on, like unable to reach server, invalid file format, or permission denied. But what if you're unlucky and there's no error message? Or the error message is super unhelpful, like internal system error. The next step is to try to isolate the conditions that trigger the issue. Do other users in the same office also experience the problem? Does the same thing happen if the same user logs into a different computer? Does the problem happen if the application's config directory is moved away? Let's say that it's the config directory's fault. You ask the user to move it away without deleting it. And now the application starts correctly. So you ask the user to send you the contents of that directory. You copy them onto your computer, and the program fails to start. Bingo. You got your reproduction case. It's starting the program with that config in place. Having a clear reproduction case lets you investigate the issue and quickly see what changes it. For example, does the problem go away if you revert the application to the previous version? Are there any differences in the strace log or the ltrace logs when running the application with the bad config and without it? On top of that, having a clear reproduction case lets you share it with others when asking for help. As long as you aren't sharing any confidential information, of course. You could use it to report a bug to the application's developers, to ask for help from a colleague, or even to ask for help from an internet forum about the application, if it's publicly available. So when trying to create a reproduction case, we want to find the actions that reproduce the issue. And we want these to be as simple as possible. The smaller the change in the environment and the shorter the list of steps to follow, the better. To get there, we might need to dig deeper into the problem until we have a small enough set of instructions. Once you have a reproduction case, you're ready to move on to the next step, finding the root cause. When you first come across these concepts, it might seem that once you have a reproduction case, you already know the root cause of the problem. But more often than not, it's not true. In our overloaded server example, we figured out that the backup system was blocking the websites from working. And so we mitigated that immediate problem to unblock the user. But we didn't really look into the root cause of our server being stuck. This could be because the network bandwidth is saturated, the disk transfer is too slow, the hard drive is faulty, or a bunch of other reasons. We also didn't do anything to make sure our backups could run successfully in the future. Understanding the root cause is essential for performing the long-term remediation. So how do we go about finding the actual root cause of the problem? We generally follow a cycle of looking at the information we have, coming up with a hypothesis that could explain the problem, and then testing our hypothesis. If we confirm our theory, we've found the root cause. If we don't, then we go back to the beginning and try a different possibility. This is where our problem-solving creativity comes into play. We need to come up with an idea of a possible cause, check if it's correct, and if not, come up with a different idea until we find one that explains the problem. Our ideas don't come out of a void. To get inspired, we looked at information we currently have and gather more if we need. Searching online for the error messages that we get or looking at the documentation of the applications involved can also help us imagine new possibilities of what might be at fault. Whenever possible, we should check our hypothesis in a test environment instead of the production environment that our users are working with. That way, we avoid interfering with what our users are doing and we can tinker around without fear of breaking something important. Depending on what you're trying to fix, this might mean we have to try our code in a newly installed machine, spinning up a test server, using test data, and so on. It can take some time to get this set up, but the extra safety is definitely worth it. Even when it seems that the error might be related to the specific production environment, it's always a good idea to check if we can reproduce the problem in a test environment before we modify production. In our overloaded server example, if the problem was with the hardware, we wouldn't be able to replicate it with a test server. In that case, we would need to either wait until the services aren't being used, or bring up a secondary server, migrate the services there, and only then look at what's wrong with the computer. On the flip side, if the problem is related to some configuration of either the web services or the backup service, we'd still see it in the test server. So we'd always start by setting up a test instance of the service and checking if the problem replicates there before touching the production instance. So say we have a test server running the same websites. When we start the backup, we see that the websites stop responding. This is great because we have a reproduction case, and we can debug it properly. How do we find the root cause? One possible culprit could be too much disk input and output. To get more info on this, we could use IOTop, which is a tool similar to Top that lets us see which processes are using the most input and output. Other related tools are IOStat and VMstat. These tools show statistics on the input-output operations and the virtual memory operations. If the issue is that the process generates too much input or output, we could use a command like ionice to make our backup system reduce its priority to access the disk and let the web services use it too. What if the input and output is not the issue? Another option would be that the service is using too much network, because it's transmitting the data to be backed up to a central server, and that transmission blocks everything else. We can check this using iftop, yet another tool similar to Top that shows the current traffic on the network interfaces. If the backup is eating all the network bandwidth, we could look at the documentation for the backup software and check if it already includes an option to limit the bandwidth. The rsync command, which is often used for backing up data, includes a -bw limit just for this purpose. And if that option isn't available, we could use a program like Trickle to limit the bandwidth being used. But what if the network isn't the issue either? Remember, we need to put our debugging creativity to work and come up with other possible reasons for why it's failing. Another option could be that the compression algorithm selected is too aggressive, and compressing the backups is using all of the server's processing power. We could solve this by reducing the compression level or using the nice command to reduce the priority of the process in accessing the CPU. And if that's still not the case, we need to keep looking. Check the logs to see if we find anything that we missed before. Maybe look online for other people dealing with similar problems related to interactions of the backing up software with the web serving software. And keep doing this until we come up with something that could be causing our problem. I know this sounds like a lot of work, but it's usually not that bad. In general, by using the tools available to us, we can find enough info to land on the right hypothesis after only a few tries. And with experience, we'll get better at picking up the most likely hypothesis the first time around. Up next, we'll talk about a tricky type of technical problem that we all have to face: intermittent issues. Have you ever tried to solve a problem that happened only occasionally? Maybe you've dealt with programs that randomly crash, laptops that sometimes fail to suspend, web services that unexpectedly stop replying, or file contents that get corrupted, but only in some cases. Bugs that come and go are hard to reproduce and are extremely annoying to debug. If you work in IT, you've probably had your own dose of frustration while dealing with intermittent issues. So what can you do if you're trying to debug an issue like that? The first step is to get more info on what's going on, so that you understand when the issue happens and when it doesn't. If you're dealing with a bug in a piece of code that you maintain, you can usually modify the program to log more information related to the problem. Since you don't know exactly when the bug will trigger, you need to be thorough with the information that you log. For example, I recently had an issue with a service I own. It was crashing sporadically, and I was at a loss trying to find out why. Looking at the error message, I knew it had something to do with strings that use special characters, but I had no idea where the bug was exactly. So I added more logging information to the service around the inputs and the function calls that I suspected could be involved. The next time the program crashed, I was able to identify the part of the code where it was missing the proper handling for the encoding and fix the problem. If you can't modify the code of the program to get more information, check if there's a logging configuration that you can change. Many applications and services already include a debugging mode that generates a lot more output than the default mode. By enabling the debug information in advance, you can get a better picture of what's going on the next time the problem happens. If that's not possible, you'll need to resort to monitoring the environment when the issue triggers. Depending on what the problem is, you might want to look at different sources of information, like the load on the computer, the processes running at the same time, the usage of the network, and so on. For bugs that occur at random times, we need to prepare our system to give us as much information as possible when the bug happens. This might require several iterations until we get enough information to understand the issue. But don't lose hope. Most of the time, you can finally get to the point where you can actually understand what's going on. Sometimes, the bug goes away when we add extra logging information, or when we follow the code step by step using a debugger. This is an especially annoying type of intermittent issue nicknamed Heisenbug, in honor of Werner Heisenberg. He's the scientist that first described the observer effect, where just observing a phenomenon alters the phenomenon. Heisenbugs are extra hard to understand because when we meddle with them, the bug goes away. These bugs usually point to bad resource management. Maybe the memory was wrongly allocated, the network connections weren't correctly initialized, or the open files weren't properly handled. In these cases, we usually need to just spend time looking at the affected code until we finally figure out what's up. Yet another type of intermittent issue is the one that goes away when we turn something off and on again. There's plenty of jokes related to how, in IT, a lot of what we do to solve problems is just turn things off and on again. And okay, it's true that in many cases, power cycling a device or restarting a program gets rid of whichever problem we were trying to fix. But why is that? When we reboot a computer or restart a program, a bunch of things change. Going back to a clean slate means releasing all allocated memory, deleting temporary files, resetting the running state of programs, re-establishing network connections, closing open files, and more. If a problem goes away by turning it off and on again, there's almost certainly a bug in the software. And the bug probably has to do with not managing resources correctly. So, if an issue goes away after a restart, it's a good idea to try to figure out why that is, and see if it's possible to fix it in a way that doesn't require turning it off and on again. And if in the end, we can't find the actual reason, scheduling a restart at a time that's not problematic can also be an option. So we've looked at a few ways of getting to the root cause of a problem, like isolating causes, understanding error messages, adding logging information, and generating new ideas for possible failures. We've also talked about problems that go away on their own and then pop up again, and looked at how to figure those out. Coming up, we'll check out a practical example of understanding a problem and how to find its root cause. A colleague recently developed a small application to send meeting reminders to people in the company because someone kept forgetting to show up. The sales team was the first to test the app last week, and it worked fine. But this week, another user is trying to send a meeting reminder, and the program keeps terminating with an error. Since the colleague that developed the app is on the other side of the Atlantic, the user is asking for our help to figure out what's going on. First, let's try running the program ourselves and check if we can reproduce the problem. We're presented with a window where we can enter the date for the meeting, the title of the meeting, and the people that we want to send the reminder to. The meeting reminder that the user was trying to send was for January 13th, and the title was Production Review. As we are trying things out and don't want to be mailing reminders out with our tests, I'll set this one to send the reminders to me. Uh-oh, it failed to send the email. This means we've reproduced the issue. Let's try the reminder that the sales team sent last week, which had worked fine. In that case, the reminder had been sent for January 7th, and the title was Sales All Hands. Again, I'll send this to myself to avoid spamming people with test reminders. Yes, in this case, the program successfully sent the reminder. Which parameter do you think is at fault? The title or the date? It could be either, but I'll bet it's the date. Let's try once more with January 13th as the date and Sales All Hands as the title. Another failure. So we have a reproduction case. When we try to send the meeting reminder for January 13th, we get the failure message. But if we try to send the same reminder for January 7th, it works fine. Now the next step is to find the root cause of the issue. Why could our application work fine for January 7th, but fail for January 13th? There could be a bunch of reasons, but in general, when dates are involved in a failure, the problem is due to how the dates are formatted. In some countries, the dates are written with the month first and the day second, while in other countries, it's the other way around. To figure out what's going on, let's add more debugging information to the program. We'll open the meeting reminder.sh script, which is a script written in Bash. We see that this script is calling a program called Zenity. Zenity is the application showing the window to select the date, title, and emails. The output generated by Zenity is stored in a variable called meeting_info, which is then passed as a parameter to the sendReminders.py Python 3 script. This script then sends the emails. To get more information about the output generated by Zenity, we'd like to see the value of the meeting_info variable before the Python script gets called. Let's add an echo statement to see that. All right, let's save this and try again. This time, we'll just use test as the meeting title, as we know the problem is with the date. We see that the information generated by Zenity is split by pipes, and that the date is formatted as month, day, year. All right, that's already valuable information. Now, the next step is getting a more informative error. To do that, let's open the Python script that sends the reminders and see if we can make it print a better error. The file is long, so it makes sense to start by looking at the main function that lists the core functionality of the program. We see that it splits the parameter received in 3, then prepares the message to be sent, and finally sends it. If everything works fine, it prints a message saying that it was sent successfully. But if anything fails, it prints the error message that we've seen already. But the error message is not very useful, as it's hiding the reasons why things failed. Let's make this error more helpful by also printing the exception that generated the failure. Okay, let's save and try again. Okay, This time we see that the problem is that the date format we are using is putting the month first, but the program is expecting to have the month second, and as there's no month 13, this is an invalid date. So we found the root cause of the problem. The program is trying to convert the date, assuming one specific date format, but we're using a different format. And as we now know, once we know the root cause, the next step is to remediate the issue. What can we do in this case to remediate the problem? We could change the program to use our date format, but then the application would break for people running it in a different location. What we need to do is make sure that no matter where we run the script, the date generated by Zenity matches the date expected by Python. Fortunately, Zenity includes a parameter to specify any format we want. So we'll change the shell script to use the --forms--date--format parameter and set the format to %y--%m--%d, which is the International Standard Date format. All right, with that, Zenity will return the date in the international format. Now, we need to change the Python script to use the same format. We'll go to the function that has the format specified and change it to the same format. Great! Now the date format generated by Zenity should always match the one read by Python, and this script should work in our country and any others. Let's try it out and check if it's really fixed. Yay! We've successfully fixed the issue. Let's quickly recap what we did. We first reproduced the problem ourselves, then found which input triggered the issue and which one didn't. We then added more debugging information to the scripts, which helped us find the root cause of the problem, a mismatch between the date formats used by the Zenity invocation and the Python script. And finally, we fixed the issue by making sure that both were using the same date format. Usually when trying to find the root cause of a problem, we'll be looking for one answer in a list of many. Searching for an element in a list is a common problem in computing. There are a bunch of different algorithms that can help us find the element that we're looking for. Say, for example, you have a list that contains the data of employees that work at your company, and you want to find one specific employee. One possible approach would be to start from the first entry, and then check if the name is the one that we're looking for. If it doesn't match, move to the second element and check again. And keep going until we find the employee with the name we're looking for, or we get to the end of the list. This is called a linear search. This type of search works, but the longer the list, the longer it can take. In other words, the time it takes to find the result is proportional to the length of the list. If the list is sorted, we can use an alternative algorithm for searching called binary search. Because the list is sorted, we can make decisions about the position of the elements in the list. So the first thing we do is compare the name that we're looking for with the element in the middle of the list and check if it's equal, smaller, or bigger. If it's smaller, we know that the element we're looking for must be in the first half of the list. On the flip side, if it's bigger, we know that it's in the second half of the list. This way, with only one comparison, we've eliminated half of the list from possible candidates where the element could have been found. And then we do the same thing again and again until we find the element. So if the element we were looking for was smaller than the middle element, we look at the element in the middle of the first half. If our element is now bigger, we look at the element in the middle of the second quarter, and so on. Each time we look at the middle element of the section we're dealing with, until we find the element we're looking for. Using linear search, going through a list with 1,000 elements might take up to 1,000 comparisons if the element we're looking for is the last one in the list or isn't present at all. Using binary search for the same list of 1,000 elements, the worst case is only 10 comparisons. This is calculated as the base 2 logarithm of the list's length. And the benefits get more and more significant the longer the list. For a list of 100,000 elements, it would be 17 comparisons instead of 100,000 comparisons. But remember that for this to work, the list needs to be sorted. So if the list isn't sorted, we would need to sort it first, which takes a chunk of time. It can still make sense to do it if we're going to search through it several times, but it doesn't make sense to sort the list and then use binary search to only find one element. In that case, using linear search is simpler and faster. If you're curious about what these two types of search look like when implemented in Python, you can see a possible implementation of linear search and one for binary search in the next reading. After that, we'll talk about how we can apply the principles of binary search to troubleshooting. We called out that the binary search algorithm is really efficient when trying to find an element in a sorted list. In troubleshooting, we can apply this idea when we need to go through and test a long list of hypotheses. When doing this, the list of elements contains all the possible causes of the problem, and we keep reducing the problem by half until only one option is left. The list of elements could be entries in a file, extensions enabled, boards connected to a server, or even lines of code added to a faulty release. And with each iteration, the problem is cut in half. This approach is sometimes called bisecting, which means dividing in two. In an earlier video, we gave the example of a new version of a program that failed to start when the old configuration directory was present. If the directory contained a bunch of different files in it, we could identify the one causing the failure by bisecting the list of files. Say the old directory contained 12 different config files. We want to identify which of those 12 is causing the failure. To do that, we can create a copy of the directory with just 6 of the 12 files, and then try to start the program again. If it crashes, then the bad file is among those 6 files. If it doesn't, it's among the other 6. In the next step, we would pick 3 out of the failing group of 6. If the program crashes again, it's one of those 3. If it doesn't, it's one of the other 3. For the last 3, we can first check 2 together or just go one by one. Either way, it's 2 checks to get to the failing file. This means that with a total of 4 attempts, we can find out which of the 12 files is causing the problem. Since things in IT can sometimes be complex and intertwined, before declaring victory, we'll want to verify that the program crashes with that single file present and doesn't crash when the single file isn't present. Once we've confirmed that, we've reduced the reproduction case of our problem to a single file instead of a whole directory. Much easier to understand and figure out what's going on. After that, we can proceed in the same way with the contents of that single file, cutting it in half repeatedly until we find the specific part of the file that's causing the problem. The same process can be applied to a large variety of problems. It's very common, for example, to use it to figure out which browser extension is causing the browser to crash. Disabling half of the extensions, then checking if the browser crashes with that subset, and so on until we find the faulty extension. We can also use this technique to discover which plugin in a desktop environment is causing the computer to run out of memory, or which entry in a database is causing the program to raise an exception. We can also apply this to code when trying to find a bug that was introduced in a recent version. If we know the list of changes that were made between one version and the next, we can keep cutting that list in half until we find the one that caused the failure. When using git for version control, we can use a git command called bisect. Bisect receives 2 points in time in the git history and repeatedly lets us try the code at the middle point between them, until we find the commit that caused the breakage. And this doesn't even need to be your Git repository. If you're using open source software that's tracked in Git, you can use the bisect command to find out which commit caused the software to stop working on your computer. For example, if the latest release of the Linux kernel causes the sound card on your computer to stop working, you can use git bisect to find the commit that broke it and report this as a bug to be fixed. And as we called out when we were talking about binary search, the longer the list of items that needs to be checked, the more we'll gain by cutting our problem in half on each iteration. If it's just 5 options that need to be checked, we can simply go one by one. It won't make a lot of difference, and it might be easier to keep track of what we tried. But if it's 100, we definitely want to bisect the problem, so we can find the answer in 7 steps, not 100. When we have to test a bunch of different options to find the one that's causing a failure, we'll want a quick and easy way to check it. Even if we're reducing the amount of attempts by bisecting the problem, we don't want to spend a long time on each check. Sometimes it's straightforward. Either the program starts or it fails. But other times, it can take a bunch of manual steps to check what we want to check. So depending on what the problem is that we're trying to find, it might make sense to spend some time creating a script that checks for the issue. Up next, we'll see this in action in a practical example. We've discussed how we can quickly find out the reason for a problem in a list of possible reasons by splitting the problem in half and testing each half separately. Let's see this in action with an example. We have a program that reads data from a CSV file, processes it, and then imports it into a database. One of the users of the system tells us that the file they're trying to import fails with an obscure import error. They've sent us the file so we can try it ourselves. To call the command, we'll connect the output of cat context.csv, the file that the user sent us, to the import py command. But before we run the command, it's a good time to remember that we shouldn't test in production. And since this script is going to be trying to import data into a database, we should run it against the test database instead of the production database. To do that, we'll use the -- server flag that takes the name of the database server, and then we'll pass the test as the parameter. We see that the file fails with an importing error and doesn't give us a lot of information about what's failing. And how big is that file? We could open it with an editor and check, but we don't need to. We can use the wc command that counts characters, words, and lines in a file. In particular, wc-l will print the amount of lines in a file. So our file has 100 lines in it. That's a lot. We don't want to have to go looking through that list to find out what could be wrong, especially since we have no idea what that might be. Instead, we can try passing only half of the file to the script and check if it succeeds or fails. If it fails, then we pick up that part of the file and check again with half of it. If our import succeeds, then we take the other half and split it in 2. We could edit the file manually to add or remove the parts as needed, but that would be tedious. Instead, we can use the tools available to us to help us do that with less effort. We can use the head command to print the first lines in the file, and the tail command to print the last lines. We can pass the amount of lines we want to include as a parameter, so head-15 will print the first 15 lines, while tail-20 will print the last 20 lines. Okay, and as we saw earlier, our command reads the file to import from standard input. So, we can use pipes to connect the output of our head or tail commands to it. Let's try to input the first half of the file now. Okay, so the first half failed. Let's split it again. To do that, we'll use another pipe to take only half of the previous number. This way, in each step, we'll add a call to head or tail for the corresponding size. Head-25. This time, it succeeded. Hooray! This means that the failure must be in the second quarter of the file. Let's verify that that's the case by giving that part to our command. To do that, we'll take the first half using head, then get the second half of it using tail. Womp womp, this fails again. But that's good. It means we're on the right track. Let's split it once again. Great! Our test set is getting smaller. Let's split it once more. Okay, we're down to 6 entries, and we know that one of them is the bad one. Let's split it one more time, and then we can look at the 3 remaining entries. All right, let's look at the 3 entries left and see if we can find the culprit. Can you see the problem? This is a comma-separated file. This means that each comma is used as a separator between the fields in the file. If a field includes commas, it should be written between quotes. But in the case of the third line we're looking at here, we can see that there's a comma instead of a period after the middle initial. And this is not written between quotes. The importing script is then confused because there are too many fields in this line. Okay, let's edit the file and fix it. And now let's run our importer again with the fixed file. Yay! We fixed the problem in the file. Using the bisect method, we very quickly found which line out of 100 lines contained the corrupt data, and then we could fix it and successfully import it. The short-term remediation here is to tell our user about what we found and how to fix it, so that they can import the data into the production database. The long-term remediation is to figure out why the file was generated with the invalid field in the first place, and make sure that it doesn't happen again.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.